worksheet 14D. Basically, the design the most efficient wide flange beam, and here is the topic is design of prismatic beams, and the material is A36 steel that could be used to simply supported beam loaded as shown. Check all critical sections of the beam using an appropriate failure theory for the ductile material. Use the factor of safety of 1.2 with respect to the yield stress, and as you can see from the note here, to prismatic beam design we have 3 steps with the design based on the internal bending moment, and then we verify with the transverse shear stress, and then apply the maximum shear stress theory. And with all of this we need to draw the moment diagram first before we go to the first step, design the base on sigma actual less than sigma allowable. So with that, let's draw the diagram. So let me here, from your engineering mechanics, you can find out. I just make a note here from engineering mechanics, which is take the moments, sum of all the moment about E to find out VB and BY, and sum of all the moment about B to find out EY. So you have BY equal to 60 kips go up, and EY equal to 40 kips go up. So take moment, free body diagram for the beams. So from that we can put the support reaction at B, which is BY 60 kips and EY, which is 40 kips. And then we apply your shear and moment diagram knowledge to draw this. The shear diagram, you have start at always start from left to right, start at 0. At A we have 20 kips going down, so it go discontinuity in the shear diagram, go down 20. Between A and B, no distributed load, so the same. And then 60 kips go up, called discontinuity from negative 20 to plus 40 to have the jump 60 kips up. Between B and C, no distributed load, so the shear maintain unchanged. And at CD there is a distributed load, and the area here is 6 times 10 kips per foot, so 60 negative 60 kips. That create a change in the shear diagram. So from 40 we can go down to negative 20 to make it the change is negative 60. So you can have here up to negative 20. And then at D we have a distributed load 20 kips going down, so cause a discontinuity down another 20 kips, so it will be negative 40. Between D and E nothing, so it maintain the same. And at E the external reaction at E 40 kips go up, so it will be cause a discontinuity up, and it close at 0. So that's why we done for the shear diagram. So this one you are very expert now for drawing the shear and moment diagram. Then from that we can find out the areas under the shear curve. So that one 23, so we have that in negative 60 for that areas. And then that between BC we have 2 times 40, so we have plus 80. And of course, as you can see, the 40 and 20 here, 20 there. So we can be able to find out very simple. We can be find out that intersection is 4 with the similar triangle, and that is 2 feet. So 4 and 40, and this is triangles, divide by 2. So we have 4 times 40, 160, divide by 2. So you have that plus 80 for this area. And this is 20 negative times 2 divided by 2. So it will be negative 20 in these areas. And the last areas between D and E for the shear curve, under the shear curve, which is 40 times 2, 80 negative. So from that we can go ahead. So this is a good review for us for the shear and moment diagram. So moment. Now the moment diagram. Start at from left and always start at 0. There is no couple between A and B, so the change in moment equal to the area under the shear curve. Under the shear curve between A and B are negative 60, so we have negative 60 down here. And it now distributed load between A and B, so it will be a straight line. So you can put down this is straight line, straight line, straight line, and this is a straight line. Similarly, this is straight line. And then between BC, now distributed load, the area under the shear curve 80, so the change in the moment 80. From negative 60, it goes to 20 to become 80. To become change 80 and straight line again. So you have that is straight line. And between C and D, it's a uniform distributed load, straight on the shear diagram, and it will be a parabolic on the moment diagrams. So as you can see, it go 20 plus 80 until 4 feet from point C. So we'll have 100. So let's make down that line here, very important, the critical line there. Now, so from C to the intersection, the peak of the moment at this point where you have the small shear, which is 0. When it's shear 0, that represents the slope at that point. So that's why you have it slope horizontal there and go down to here, connect there at the moment, and go to 100. That point here, you can see 100, and that's a parabolic P for that curve. And then from that intersection to point D, it also distributed load, and it reduced 20, so it go back to 80. From 100 to 80, so you have to 80 reduce, change negative 20. And then from that it go back to negative 80, so nothing between D and E, so it will be straight line. So it will be straight line there. So we can have this is this point 80, keep foot, and that one parabolic, and this one is straight line. I'm going to see that here. So it will be straight line between this, but my drawing it's like a, so let's make sure it's straight line. Okay, and close at 0. That's perfect for our diagram. So from this diagram, as you can see, go to the next step. Is step number 1 to design for the internal bending moment. And at the internal bending moment, you see the maximum moment For this one on the moment diagram is 100 key force, and that will be the next video when we touch on really go to the design of prismatic beam from step that we have mentioned in the lesson here.